All right, so we need to talk for a few minutes about waves at boundaries. What I mean by that is when a wave is traveling through one medium and then it reaches the end of that medium and goes to go into a second medium. So maybe your bathtub is half filled with water and somehow the other half is filled with chocolate milk. Two different media with two different densities. So what happens to that water wave when it reaches the chocolate milk? Or maybe you took your Slinky and you tied a string to the end of it, and one person is holding one end of the Slinky and a second person is holding the end of the string, and you send a wave down the Slinky, and when it gets to the point where the Slinky meets the string, that's the boundary. Or maybe it's my voice, my sound wave, traveling through the air and hitting the back wall. So it's meeting a boundary. So what happens when waves come to a boundary between the two media? Well, there are three possible things. One would be that all of the energy in the original wave gets transmitted into the second medium. Okay? And this happens most often when the second medium is less dense than the first one. So when it's going from more to less. The second possibility is that all of the energy gets reflected back into the first medium. And you would expect this to happen if you're going from a less dense medium to a more dense medium. It would be like throwing a ball at the wall and the ball reflecting off. My sound wave hits the back wall and it reflects off. Very little perhaps would pass through. But in real life, what usually happens is that some gets transmitted and some gets reflected. How much gets transmitted and how much gets reflected totally depends on the differences in the densities between the two media. Okay? Now, as the wave gets transmitted into the new medium, remember its speed will change because the density is different, but its frequency will stay the same because that is set by the frequency of the source. So if the speed changes and the frequency remains the same, then the wavelength must also change. Okay? Something else kind of neat happens. If you're going from, let's say, a string into a spring, like maybe a spring in the shock of your car or a fairly heavy spring. Okay? If I send a pulse down the spring, and when it hits the boundary, some of it will go into the spring, but the height of the pulse won't be as high as it was in the string because it's going to take more energy to move the heavier spring up. Some of the pulse will get reflected back. So what happens is as the pulse reaches the spring, it pushes upward on the spring, or maybe upward like this on the spring, and the spring pushes back. And because the string or the rope, I'm going to use rope so it's easier to tell what I'm saying. So when the spring pushes back on the rope is less dense and it causes the pulse that's going to return in the first medium to flip upside down. If you were going the other way, if it was more dense going into less dense, when the pulse gets to the boundary, it's going to cause the less dense guy to have a higher amplitude. And when the less dense guy tries to, so the more dense is pushing up on the rope pushes back down, but remember this spring is more dense and it doesn't have enough energy to flip the pulse over. So when it's going from more dense to less dense, the reflected pulse actually comes back on the same side. Okay, when it's going from less to more, it gets flipped over. Okay? If it reaches a free end when there's nothing here, then that would be going from more to less again, right? Because the air would be less dense. And so anything that's reflected back should be reflected back on the same side, but it would be pretty hard to see. Okay? I want to talk about a couple of other things. One is about standing waves. Musicians might know about standing waves. All of you, if you've ever watched a guitar string, would probably know about probably have seen a standing wave. So here's my wave. Okay, here's my guitar string, here's my wave. So this wave is traveling, I strum it. It's traveling down the guitar string. I strum again. So now there's a second one. Okay? And when it gets to the other end of the string, it's going to reflect back. And when it reflects back, I'm still strumming. And so what you see, you no longer see the wave traveling down the string. Instead, you see what looks like the string vibrating back and forth like this, up and down. But the wave, so changing in position but not traveling down the string anymore. This is called a standing wave because it looks like it's standing still in the medium, that it's not moving in the medium. These points that have no amplitude, here, 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 these points are called nodes. Nodes are points of no amplitude where the medium isn't displaced. The points with maximum amplitude are called antinodes. Okay, so it doesn't matter if it's positive or negative, above or below. Okay, and so I've drawn it as a dotted line because at one instant you'll see it as a crest and as a trough. What you'll see is it moving up and down across the rest position, across the equilibrium position. You'll see it vibrating back and forth like this. You will not see the wave traveling down the string. And so if you've watched a guitar string, that's what you see happening. Okay, it's called a standing wave. How many half wavelengths it would depend on how quickly I'm strumming, right? If I change the frequency of my hand, it will also change the frequency of the wave there. Okay, so here I have, in this full length, I actually have two waves, right? One complete cycle, whether it's up or the dotted one going down, that's a wave. So this is one full wavelength. So the distance from one node to another then would be a half wavelength. Okay? So nodes, antinodes, standing waves. They'll come back up. All right. Next we need to talk about interference. Interference. Interference happens when two waves are trying to travel through the same medium, the same part of the medium, at the same time. It happens all the time. If you play a sport, you sometimes get a penalty for interference because you're trying to travel through the same space as the other person at the same time. If you've ever been in a car traveling a long distance and you have a radio station on, and then before too long, another station begins to cut in. That's the radio waves interfering with each other, the signal from one station interfering with the signal from another station. Two waves are trying to travel through the same material at the same time. Now, when that happens, we can add them together. The amplitudes are just like displacement vectors, and so when two waves are traveling through the same medium at the same time, we can just add up their displacements to find the resultant displacement or the resultant wave of what we would see or hear, depending on what type of wave it is. When we do this, it's called the principle of superposition. And you may have heard of superposition before in pictures, right? When you superimpose one picture on top of another so it looks like you're standing beside Prince Harry. Okay, principle of superposition. So we're going to look at three cases. The first case is when there is maximum constructive interference. And in